Hello everyone, I'm Huang from CISPA Helmholtz Center for Information Security. Today I'm going to present our work, Accessibility and Privacy Don't Have to be Mutually Exclusive, Constraining Accessibility Service Misuse on Android. This is a joint work with my advisor Sven Bugiel and my supervisor Michael Bacchus. Accessibility features are meant to assist people with disabilities or impairments in using their systems. To achieve assistive functions, accessibility apps need a large set of privileges that violates the purpose of Android Sandbox. For instance, accessibility apps have to be able to monitor the texture content of other apps to speak loud for people who have visual impairments, or press button in other apps for people who have mechanical impairments. Android provides dedicated permission for accessibility service. However, this permission is not fine-grained and cannot provide further restrictions once approved by the user. Since the accessibility service is so powerful, it is not only useful for assistive apps, but also for a lot of other apps, such as utility apps whose users don't have actual impairments, but do use it for innovational functionalities. Also, malicious apps are using it. There has been a lot of research and news of malicious apps misusing the accessibility service to harm the user. For example, to steal data, to silent install applications, and so on. Here comes our research question. Can we design accessibility APIs in such a way that we can protect the user's security and privacy while still making them usable for those who rely on them? That leads to another question directly. How do we distinguish good from bad behavior? How do we distinguish benign usage from misuse of accessibility service? To answer this question, we started by investigating the actual usage of accessibility features in real-world apps. We categorize apps integrating accessibility features into malicious, utility, and accessibility. Malicious apps take advantage of accessibility features to attack the user. Accessibility apps use accessibility features to assist people with disabilities or impairments. Utility apps are neither typical assistive apps nor malicious. They are using accessibility features for user-desired functionality beyond supporting people with disabilities. From Google Play's top list and the renowned malware GitHub repositories, we collected 95 accessibility app samples in total. First, we checked accessibility service misuse from benign usage purely based on the configuration that those apps have. From the configuration, we can see which events they want to monitor, how much they consume, and how invasive they are to the user's privacy potentially. Our results show that we cannot distinguish apps purely based on the configuration, because all three app categories have a very similar configuration and are monitoring broadly. Since we cannot distinguish apps at the configuration level, as the next step, we try to distinguish misuse from benign use based on API usage. We want to know which API they are using and are they retrieving information to perform some UI actions like clicking a button or going back to the home screen. Unfortunately, again, the answer is no. Our result shows that all app categories show similar patterns in how to retrieve information from other apps and how this leads to certain UI actions. Thus, based on API usage, we also cannot distinguish good from bad behaviors. So we further zoom into apps to investigate the various events that trigger access to the accessibility framework, how data retrieved from the accessibility framework is used, and to which sink such data flows. We call those app-specific combinations of triggers and usages the app's accessibility pipeline. Here is the result. We found that no matter what the trigger is, evaluation of whether a trigger condition is met or resides entirely within the apps. We also found that 2 out of 4 prominent intended operations in accessibility apps overlap with the intended operations in malicious apps. Apart from that, Although the intentions of screen reader and the content eavesdropping are not the same, all of them require raw data processing within the app. We also found some differences between pipelines. First, we noticed that although some apps from different categories share the same intentions, accessibility apps usually require more powerful accessibility functionalities. It means that malicious apps can be easily overprivileged without raising immediate suspicion. Second, both benign and malicious apps require raw content processing within other components of the apps, but their final data destinations are different. We also found that malicious apps are more likely to perform operations silently or against users' intentions. The key finding of our study is that the complete accessibility pipeline is distinguishable between app categories when being able to detect the combination of which trigger lead to which action or data leak. Benign apps can distinguish themselves from malicious ones through different data destinations in combination with explicit user-consented node actions. So a potential solution that makes accessibility and privacy not mutually exclusive could associate the UI operations by an accessibility service with user intentions to avoid covert malicious node actions, or at least withhold crucial information for efficient malevolent node actions, and prevent the on-screen information of apps that is gathered through accessibility framework from being misused by malicious accessibility apps. For example, screen reader can consume textual information from the accessibility framework as input and can write arbitrary output streams to audio things. To avoid the screen information from leaking or the app from issuing malicious node actions, it should not be allowed to issue node clicks or use any other output channel. Thus, it can work as intended as a screen reader while preventing sensitive data leakage or the repetitious interactions with other apps. Here comes our solution. We can treat the accessibility pipeline of accessibility apps as a sequence of steps and redesign the accessibility framework such that those steps are made explicit. And each step's privileges and I/O can be individually governed by a least privilege privacy policy. However, the content of each step is treated as a black box. By keeping the overall pipeline in mind when authorizing the privacy policy, we establish control over the possible data flows of accessibility apps with a suitable policy that allows benign flows to proceed while preventing potentially malicious flows. Privacy protection and enabling accessibility services do not need to be mutually exclusive anymore. This is the design of our framework. The accessibility pipeline is a sequence of connected individual steps and applies flow constraints to control the data flows along the pipeline to prevent unauthorized data leaks or actions. Although this accessibility pipeline logically exists in real-world apps, clearly distinguishable modules do not necessarily exist. So the first thing we need to do is retrofitting the current accessibility app and making each module distinguishable. Usually, the front-end module gathers user intentions from sensors or peripherals. Accessibility modules perform UI operations or retrieve sensitive information via accessibility framework. Backend module creates the output of the pipeline. After making each pipeline step explicit, we need to apply the least privilege privacy policy to each step. We first transfer design concept for privilege separation to our solution. By default, all code running within the same app sandbox would share the same privileges. Thus, to privilege separate untrusted code, it is moved into a separate sandbox and running under another UID, which has a distinct set of permissions and access rights. We apply this idea to our framework and compose our accessibility pipeline with each module running in its sandbox. Now we can control which resources or APIs each module has access, and designating each module for a certain step in the pipeline makes the overall process more transparent. After sandboxing each pipeline module, the original local module calls are now IPC calls. In our solution, we let components of the accessibility app that are outside the pipeline connect modules and orchestrate the pipeline. Each module exposes its own IPC interfaces to those app components. To further prohibit unauthorized accessibility data and action access, we take inspiration from opaque handles for IoT apps and the recognizers in augmented reality app data processing pipelines to apply more constraints to flows along the pipeline. We evaluate our framework with two open source accessibility apps. For TalkBack, we split the screen reader components into two modules. As this figure depicts, after migration, the accessibility module can detect touches, but it cannot leak anything. The only thing it can hand out is a handle to text. The backend can declassify the text, but it has no idea where on screen it came from. It cannot actually leak the text, but the only thing to which it can leak is the audio output. Neither the accessibility module nor the backend module by themselves can do any harm. The data they can change is the only data we want to declassify. You can find more information about facial mouse and the performance evaluation in our paper. Now let me conclude our work. Accessibility service is so powerful and unconstrained at the current Android, so that it's easy to be misused. And all the existing solutions make accessibility and privacy mutually exclusive. Our work proposed to treat the accessibility pipeline as a sequence of explicit steps and try to control data flows between steps. With our solution, we made the first step towards making accessibility and privacy not mutually exclusive anymore. Thank you for your attention.